Okay, let's finish up this set of lectures on curves and surfaces by looking at some examples of rendering the famous Utah teapot. So what we're going to do is I'll show you a couple of ways we've done it, both with recursive subdivision and polynomial direct evaluation of the polynomials for the Bezier curves and surfaces. And at the end, I'll show you two variants that use what we've already talked about adding lighting and shading to our teapots. So if you look at this data set, it really is the most famous data set in computer graphics. It goes back, I believe, to the 60s. Mike Newell at the University of Utah created it because Utah at that time was doing extraordinary work in computer graphics, and just some of the very best people in computer graphics. They all came out of the University of Utah at that time, which was where Ivan Sutherland had gone, who had started all of interactive computer graphics at MIT, went on, was a faculty at Utah for a while. And this data was actually from a real teapot, and it was divided up into 32 Bezier patches. I believe that those patches are for half of it because it has symmetry. If we look at this as being the x and the y directions, it has symmetry about the z equals 0 axis, so you can just get the other half of it by just reflecting that half. There's various data sets around the web. They're all broken up into two parts. One is the 306 vertices. In the older versions of this, everything was numbered starting at 1, because this goes back to the days of Fortran, and so be careful if you pick up some of these data sets on the web. Some people, like the ones I've always used, I've converted all the indices up to starting at 0 instead of 1, but be careful of that. So there's 306 vertices that are measured points on this teapot that are given just as x, y, z values. And then there's a list of patches, of 32 patches that divide, that each is a Bezier patch that are given by their indices. So it's sort of a vertex index representation that are just references back into this list of 306 vertices. Now, a couple of things you can notice here. This is obviously just the wireframe implementation, but a couple of things I want to point out is that you could see where the patches are. They put a lot of them up here on the lid because you wanted to capture the curvature of this little area, and the same thing on the spout and the handle. Which is okay for if you're just going to shade this with some polygons and shading and lighting. It's problematic for things like texture mapping, because if you say, well, this is what you're seeing here on the body here is probably 4 or so patches because it doesn't change very rapidly. But if you now map the same texture, suppose I wanted to put something like the cube texture on this teapot, the problem would be that here I'm spreading a texture out over a fairly large area. Here, where I need a lot of patches to get close to the curvature, I'm going to take that same texture map, at least in a first try, and now spread it over a very small area. And you really notice that. So you see fairly large checks here and very small checks here, which is certainly not what you would expect to see if you had that pattern on a real texture. So it brings up some of the issues we just mentioned briefly when we're talking about texture mapping, of the need to scale the textures correctly for the size of the patch that you're really working on in whatever space you're using. And there's various techniques for doing that. I mentioned some in the textbook about whether you get your coordinates in object space or you get them in camera space, but you could see why these difficulties are going to arise. But let's leave that for now and just talk about rendering this first with curves and then little polygons displayed only by their outlines or edges, and then later by using lighting and shading. So if you take the teapot data set, what I did is I created from the original data, which just lists some numbers, I created some JavaScript that you can use that's on the website, because these are really fun to work with. One of the things you can do now is you can really do a lot of things with shaders. And one year, SIGGRAPH had a contest for the most interesting ways that people could render the teapot. So people were exploding the teapot and rendering it in all kinds of bizarre ways. But with programmable shaders, you can actually do a lot of that pretty easily. So, for example, if I said I wanted you to explode the teapot, you'd be able to have different pieces of it going off in different directions by just creating a little shader that changed the vertices as they pass through. So this is a fun data set to work with. Now the way I've put it into JavaScript was into two files. One is just vertices.js, and I create two things called vertices and patches. First one in this data set. So all it is vec3s of the 3D points that are in the original data set, which, as I said, was just a list of these line by line. And one of the things that you can do with this is, because these are just JavaScript files, it allows you to use this data with any other program that you want to write, because all you need to know is that the data is in something called vertices and something called patches, and that the number of this var number of teapot vertices has the number of vertices that are in there. So lots of ways you can use the same code to do any other data set that gives you something called vertices and something called patches. So the patches look like this. Obviously, this is a JS where you have 32 patches, and you just you output something called indices, which are just 32 indices going from 0 to 31, each of which have 16 pointers back into the array of vertices. So this one is just the first 16 numbers, then it starts getting a little more interesting for the other patches. So so I use these in all of my examples. I think there's 5 different versions of this on the website for chapter 11. Here's an evaluation done using a lot of subdivisions and just directly evaluating the polynomials, and then using 3 vertices to define triangles. So there's a whole lot of triangles in here. No problem to render, though. So first thing I did is to create a little function that you give it a value of the parameter, and it gives you a value of the Bezier function for that u. And notice this one is actually not particularly efficient, because I'm not using Horner's method here to evaluate the individual things. So it's just a very simple thing that creates an array B for that and returns it for that. So B of Bezier of a given u is going to give you the Bezier evaluation for that value of u. So that one's pretty straightforward. Now, in order to render this thing, I've got to go from the vertex indices to the actual values of the vertices. So here's a little piece of code that will let you, for any node, which will now just take the indices, number of patches, and go over the number of patches, create an array of 16 values to put it in. And here's what I'm trying to do, is just create a vec4 for pointing into the array of vertices using indices of ij, and then take the x, y, and z elements and put them in there. 2 little things here. One is I'm creating a homogeneous coordinate point, so I'm making the 4th variable 0. Second little change here is that the x, y, and z directions are different in the original data set. We're pointing y straight up. There's a lot of which is pretty common now, an x to the right, z going in and out of the screen. A lot of the older stuff has z going up and z going up, and a y pointing into the screen. So I just did the flip here in this conversion. You probably want to do that, or your teapot is going to be lying on its side. Okay, so now I can take these data and now use the actual x, y, and z data rather than the indices and now create the data that I want. So this thing is now evaluating the Bezier over, I can decide how finely I want to subdivide it, create arrays to put the values in. I'm creating little quads to put so I can render it either by rendering it as a line loop or rendering it as filled polygons. So I'm creating little quads here, and then just setting the data, using the number of subdivisions I want each time, creating an XYZW array. So this is pretty straightforward. It's using the functions in MVJS to do the scaling. The scaling factor is gotten by evaluating the Bezier in both U and V. And so this is, I think, pretty straightforward. There's just a lot of data sort of index going on. But eventually what you wind up with is just a data array, and now I can go through that data array and push the data onto an output array for the vertex buffer object. And here's standard thing. Once I've got it all set up, I can just go over the number of little quads that I'm going to get and put those data in, now indexing by X and Y. I've done this putting 2 triangles in for each quad, but obviously you could, if you wanted to render this with any other triangle format, you could have done this with 4 by using using either way. We've been doing it all along. And if you then do this, you get, here's with fewer subdivisions than before. Here's a little recursive subdivision of that, and it pretty much looks like what you had before. You still got a lot of polygons on these, on the lids and on the handle and spout, but this is pretty much equivalent to what we had before. Just the lines look a little thicker because I blew them up from a lower resolution. Now, so that's sort of the direct way to go about it. Just evaluate the polynomials at all the points you have to and do it. Here's a recursive subdivision way of doing it, and this should look pretty much exactly what you had on when I derived the algorithm in the previous lecture. I start with the data for that determines a Bezier curve. I'm going to return a right and a left curve, and they're obtained by doing the subdivision before. So mix is the division by a half. I'm not doing anything here to sort of do it in hardware where we would replace multiplications by 0.5 and divisions by a half by shifts. Doing it by just using our mix function. I'm computing these are exactly the equations that I had that are in the book and there. So it's pretty simple to do. Here's a recursive subdivision. It's giving me 2 curves. Now I can, once I can do this, now I can apply those to patches by doing exactly what we talked about in the last lecture. So there's a little more code here. I won't go into it in any detail, but what you're going to do is subdivide, remember, in the U direction. You're then going to subdivide in the V direction. That's going to give you 4 groups of 16 points, and then I recurse on each of those until whatever my stopping criteria is. I think the way I've done this example is to just do it for a fixed number of subdivisions, not worrying to test how big that convex hull was. So I'm creating a bunch of matrix 4s because that's what I'm going to do, 4 by 4s to include the data. So there's a divide patch function, which is the key to all of this, and that's going to use the divide curve function to give me the subdivisions in both U and V. So I set it all up. I go through this here. I subdivide in one direction. I then transpose the data, which means I could essentially go through exactly the same thing by switching U and V through the transpose. I do the curve subdivision again, and eventually when I finish all of these curve subdivisions, I have all of my groups of points stored in these various arrays that I've created, and now I recursively subdivide those. If count was not equal to 0, I would subdivide those patches, and eventually if I get down to count equals 0, I draw the patch. Well, what does draw the patch really amount to? It's pretty much what we take the data, and here's draw a patch. What I do is essentially push exactly the same data that I was doing for the polynomial case into my vertex array called points here, and I keep track of how many times, how many indices I've created. So the rendering now is no different than rendering any other array of x, y, z values that we've done before. So in fact, this function here is pretty much what we had for the polynomial one. Really, the action is all over in here of doing recursive subdivision of the 4 patches by subdividing the curves that make them up. Okay, so that's a lot of code, but I think in principle what we're doing is pretty straightforward. Now, what about adding shading? Well, look, at this point, once I have the data arranged in these quads or 2 triangles each, then rendering them is no different than anything else I've done with lighting or shading. The only little twist here is, what do I do to get the normals? So let me finish this by showing you 2 examples. In this one, what I've done on the right is to use what we call face normals. All we do is use the data to determine a normal that's constant over the entire patch. Well, how do I do that? I can take the 4 points, I use one corner, so call that the 0, 0 corner, and then compute vectors in 2 dimensions that lie in this patch, assuming it's flat. I could do this for each triangle, by the way, if I want. There's no problem. So suppose I have 3 points on the triangle. I can take the point here, which is fixed, use the point on the right to determine a vector in the tangent plane, a point above and the fixed point to obtain a second independent vector in the tangent plane. Take their cross product, normalize it, and that gives me the unit normal to this patch, and use it over the entire patch, either by creating a vertex array where for each point I also store the same normal, or I can even think of just sending over as a uniform that normal for each patch. For this example, it doesn't make much difference. But what you do notice here that is kind of nice is that you see, even at this subdivision level, even on the handles, it's a little too bright here to see it. You can see it on this knob here, that you really do have problems with. This is problematic probably because I'm using a triangle fan up here. But if you look at what's here, you obviously can see each patch because of the constant shading on each face, which is made even worse by the Mach band effect of seeing when you have a transition between something that's brighter and something less bright. Your eye makes it overshoot at the edge. So along this edge here, for example, it's darker along the edge and then sort of visually retreats to a level that's a little less over here in the middle. And on the right, you actually see this as being brighter just to the right and then retreating. This is actually not in the data. It's not on numbers that I'm displaying here. It's actually something your eye does to enhance edges, and that's why it's useful as a human to have that. But this enhancement of edges means that you need a higher resolution sometimes than you think in order to make things look smooth. So here on the left, what I've done is I've now used the exact values at each vertex for the normals, which I can do, as I said in the last lecture, by just taking the equations for the Bezier curve, differentiating them with respect to u and v, since they're polynomials in u and v, no problem doing that, then taking the cross product of those polynomials to give me the normal vector, which is again just going to be the product of polynomials in u and v. And notice that here, even though the number of subdivisions is exactly the same in these 2 cases, now I have this very smooth rendition, but I can you can see the level of the subdivisions kind of being the same, because if you look at the silhouette edge around here, which is on the top rim, which is the edge of those polygons that's determined by the resolution of the polygons, rather than how many subdivisions I do, rather than by any tricks I can do with the normals, you still notice it here, you notice it over here actually too. Okay, so what does the code look like? Well, the additional code is pretty simple. Here's the computation of the face normals that are going to be constant across each face. So I simply take the difference of the two data points. I do take the cross product. I normalize that. Because they're normals rather than points, I'm going to set that fourth value, the W value, to be 0. And now I just push that normal value onto an array normals, and because I want it to be the same for every point, I'm just going to push the 6 times on that. And again, here I could have been a little more efficient of storage by simply sending out these normals, but here I think it's a little easier to see what we're doing. We're pushing it, the 4 data points on to define 2 triangles, and the same normal for each XYZ value. And that's how I got that first rendering. Now, if you want to use the exact normals, here's the differentiation of the polygon. So here's the Bezier differentiation. So I differentiate the u cubed term, I get 3u squared. I differentiate the u squared term, I get this value. So I differentiate again, I get this one, the 3 from the original function. And so this is again the different derivatives with respect to just u, but by substituting u and v, I can take the product at any point that I want, and that's how I generated the normals. So then in the normal array, I'm pushing not a constant normal, but a normal that I get by taking the cross product at that value of u and at a value of v and putting that value into the array. So the code is almost the same except for this computation. So that's how we can do it. Now, I want to finish this lecture by saying a couple of things about more advanced shaders that are not available yet in WebGL but are available in Desktop GL, OpenGL, which, you see the problem here, hopefully they'll get around the following problem. In the problem here, everything we're doing is being done in the CPU. So even though I'm generating a lot of vertices and other vertex data like the normals to get this rendering, it's all being done in the CPU, and I'm sending it all over to the GPU. Now, I can do certain things pretty efficiently. Then I could do rotations and things by just leaving the data there and sending over rotation matrices. And so the rest of the code that I haven't shown here, the model view that might be changing in time, all the lighting parameters, that's no different than anything that we've done so far. So don't have to show you that here. But what you'd really like to have is the ability to take the data and not, let's come back, let me come back here for a second. Not take all the original data, well, just use the original data and not all the subdivided data, which is a lot more data than I originally started with. Originally I had the 300 vertices. That's really, in some sense, all I should have to put onto the GPU, and not all of these thousands and thousands of subdivided vertices. So what you can't do that quite the way you want here, because for a curve you need 4 data points to determine this function of u, and the way that GPUs work is, let me come over here, talk about geometry shader, is that each vertex is processed independently, and you send one vertex in and out comes a single vertex. And so I'm sort of in this problem that I have four data points which I can look at as vertices, but this doesn't fit how our standard vertex shader works. Well, what was done was that the OpenGL created what are called geometry shaders, which allows a vertex to get more data. So you can do that now. You could send a single vertex over and send the other 3 vertices over, but you can't output all you want. See, I could send, by making the other 3 vertices be other attributes, call them P1, P2, and P3, and P0 sets off the vertex shader. But the problem is I can only output a single vertex, so that fails. However, with a geometry shader, we can do exactly that, send over the 4 control points, and tell that geometry shader how many vertices I wanted to produce. So I could put all of the kind of code that we just discussed into a shader, and then that geometry shader will produce as many points as I want, and each one of those will trigger an execution of a vertex shader. So the geometry, so data goes to a geometry shader. Geometry shader generates a lot of vertices, but each of those vertices triggers an instance of a vertex shader, so that everything is happening now in the GPU rather than happening in the CPU, and I have far less data actually stored on that CPU. So that's something that's supported in desktop OpenGL and any of the recent versions. It'll probably come at some point into ES and then come into WebGL. Now the other kind of shader that came about was called a tessellation shader, where you can do much more complicated things. You can take a whole bunch of data, and that data can define a more complex mesh. If you think about what people really do, is they really work a lot with meshes, and meshes can be pretty complex. They can have topological issues like having holes in them, and then you worry about things that we talked briefly when we talked about meshes, that you have to worry about winding numbers and which direction. Actually, I'll talk about this more when we talk about implementation, is which direction you're circling the vertices and whether a hole goes one way or the other way, and you can have polygons inside or meshes inside other meshes. So tessellation shaders, or shaders where you can send it a whole bunch of data, and then it'll output triangles, but it'll understand complex things like having holes inside of that mesh. And that tessellation shader, complex to use. It actually uses two shaders as part of it that are special. It's not yet in ES. Probably not only just that they haven't gotten up to it, but it's a question whether you really want to support that or can support that on mobile devices, especially on very low power kinds of devices. Now, what's happened recently is the advent of another type of shader called a compute shader, which is not like any of the other shaders at all. It's essentially this compute engine which can use the power of the GPU. Remember, we were talking about GPU. Well, this is saying, well, knowing that I have this tremendous floating point capability on the GPU, I'd like to send it over to do some computations that could then result possibly in some geometry. So it's not necessarily being triggered by the geometry the way a vertex shader is, and ultimately a fragment shader, but it's something that's out there that lets you do computation without going to a whole other kind of system like OpenCL. And that was just announced last week, that the release of ES 3.1 and 3.1 has a compute shader in it. So it sort of says a couple of things. One, that this kind of computational power is coming down the road to WebGL, but also it seems to be saying that geometry and tessellation shaders are probably not as important as our compute shaders, and so hopefully within the next year or two we'll see a new release of WebGL that'll start having some of these features in it.